Right. So as we discussed in the earlier class, we have basically the hardware at the bottom layer, the hardware that constitutes the bottommost layer in your machine. This is the system. This is your machine. Say PC. C is just one type of machine. It's a computer. But inside the hardware, the bottommost layer is the physical device. We also have two logical layers. These are logical. And the physical layer is right at the bottom. So both this physical layer and the logical layers together, they constitute the hardware. Because any hardware that needs an interaction with the software, with a bunch of logic, needs to be associated with a microarchitecture. And as I mentioned in the last class, the microarchitecture is all about mapping. So you have to develop a map, right? Like I give you a plot of land to do something, to do gardening. But the first thing you need to do is to create a map of the land. Only then, after that, you can
Dạ cuối cùng
logically
ngồi xem
do
ông dạy học
something
này và kiểm tra
in
cuối cùng.
different parts of
Cuối
this
cùng
plot
ngồi
of
phút
land,
giây.
turn it into a beautiful garden, flower garden. So that's what microarchitecture is all about. Any hardware is associated with microarchitecture. And depending on this microarchitecture, because it varies uh, on from system to system, on two counts. One is the kind of underlying device that you have, and also the purpose this, of that machine. So depending on these two factors, this microarchitecture differ from one uh, hardware, one machine from another machine. We have different kind of operating systems because operating systems essentially interact with the microarchitecture. Well, interacting with the microarchitecture, I shouldn't use the word interacting. They basically interact with the physical device. But to interact with the physical device, they need to know the microarchitecture or the map of the physical device. As we go deep inside this chapter, in different chapters, whenever we have different interactions happening between the kernel modules and the underlying hardware, for different hardware, we'll be referring to these different microarchitectures. On top, the operating system is essentially, it contains parts. It has two parts. One is what we call the kernel, which is the core of the operating system. We say core because most of the important modules of code, and don't forget that operating system is a software, just like any other software, it's a software. And actually, this software too is full of codes and full of modules of codes. So some of the vital modules that contain vital codes that take actions related to control and coordination. Between all the interactions between the hardware and the software, basically the users. So these codes are residing inside the core of the kernel. That is what's called core of the kernel. In most cases on the slides, for your easy understanding, we will give you the schematic diagram that you can see in front of you, which kind of gives you an assumption, a feeling that it's all layered, like the bottom layer, and we'll even use these words. The bottom layer is the physical device, and then we have a microarchitecture. Then on top of that, we have the operating system, the core of the operating system, the kernel, and then on top of that, we have the user node. That is what we call the user node. But in reality, we understand that this is all logical. The operating system is nothing but another software. So there is in a software, there is no upper layer or bottom layer. So essentially, a software is just like this. It has multiple modules of codes. And these modules of codes are constantly interacting with each other, or passing the control from one module to another module. That's the way any software runs. OS is no exception to that. Some of these modules take up the role of the kernel because they constitute the core part of the OS, because they contain the vital codes that are needed to facilitate this interaction with the underlying hardware. And the others will take care of these runtime environments. Runtime environment means the others, which we call casually the user mode of the operating system, the other modules codes inside the operating system, modern operating system, they will facilitate the runtime performance of all the user level applications or software or application software. And we are right here. We, the users, we are right external to the system. So we interact with the application software. The application software from time to time need a service from the underlying hardware. So they will have to send a service request to the operating system. And the operating system's kernel mode or the kernel codes will facilitate that interaction. That's the way your OS works. Clear? As you can see right here, very simple. This is what we call user mode. And this is what we call the kernel of the operating system. In general, when we refer to operating system, with the word operating system, it means the kernel, the core of the operating system. Because the user mode, essentially, as you said, that in the older versions of operating systems, like MS-DOS, we didn't even have any. But now in the multi-programming environment, the user mode is becoming more and more important because performance is becoming an important issue. The speed of performance. In older machines, the speed of performance was not the focus. The focus was performance, the correct output. Machines were a little slow or a little fast, it didn't really matter. But now, in modern computers, speed is definitely one of the most decisive factors. So naturally, the user mode is gaining more in importance, gaining in importance more and more. So what is an operating system? Well, you can say it's an extended machine, kind of a virtual machine. That's too much of an extended idea. But it hides the messy details which must be performed to facilitate this interaction. It also works as a resource manager. And that is interesting because when someone asks you that, can you tell me what is going on inside this computer? In a very casual way, you can say that it is inside the computer, it's all about processes and resources. Chiefly hardware. So there you are. The processes, as you understand, they're asking for resources, they need resources for execution, for their execution. And at the same time, the resources, the same resource, is being requested by multiple processes. And one process might be holding on multiple resources at the same time. So we need a manager right here, because this manager will essentially coordinate and control the distribution and allocation, allotment, that is what we call the allocation and acquisition of resources.
Allocation is
To
which
and
one
by the
main?
process. So if a process needs to get a resource, it will have to send a request to the manager. And who is the manager? Of course, the operating system.
What's mean?
The manager will logically assign that resource to that process. And finally, the process will go there to acquire the resource and use it and release it when it's done. And only after it has finished and it has released the resource, then immediately another process, which has also been allocated, which has also been assigned to that resource by the manager, will now jump in and acquire that resource. And that is where sometimes we run into conflicts. Conflicts happen because one process, the process one, is currently using resource one, and process two is waiting. But process two has already been given the green signal by manager, because the kernel or the manager just assigns something. So the process two jumps in and wants to acquire resource one. Two processes inside one resource, it is deadlocked. Your machine hangs, resource hangs, and resource becomes unresponsive, and these two software become non-responsive as well. And we encounter these problems all the time. In older computers, in our times when we were students, 2 or 3 times a day, your computer or computers used to reboot, used to do auto reboot, used to crash. Crash was so common. But now, of course, the algorithms inside those operating system codes have become strong enough to prevent a crash, which is not a welcome thing, both from the hardware point of view and from the software point of view. So they are capable of controlling or minimizing this crash. And as sometimes we still run into conflict, as you see, that non-responding. So what do you do? Well, we guys are very impatient. Okay? Thanks to computer, we have become more impatient. If we have a little bit of patience, the best thing to do when you see that they are non-responsive is to leave it alone. Leave your computer alone. Don't touch the computer. Don't even click the mouse. Don't even press the key.
Don't leave the mouse.
You will see if you leave it alone, 2 minutes, 3 minutes, 5 minutes later, that non-responsive process has suddenly become responsive. But as I said, we are just too impatient. 5 minutes is a big time. 2 minutes is a big time for us. So what we do the worst thing possible. We keep hammering on the keyboard or even Control-Alt-Del, kill the process. But those things are not good because the kernel is designed in such a way that, well, why, after waiting 5 minutes, the previously non-responsive process became suddenly responsive? Why? Because something was happening behind the scenes, deep inside your computer. It was the operating system which was trying, the resource manager, which was trying to resolve this resource-related conflict. That is the most common example that we get. Okay? I love these two sentences. Each program gets time and space. As I say, the first they will have to go to the manager to request the resource. The manager will give them a time and will logically assign that resource to that process. But remember, logically assigning the resource doesn't mean the process can immediately go there and get it. There is the root of the problem. We will talk about it in details in the second chapter a little bit, and also in the last chapter, deadlock. It's very, very interesting if you really enjoy the operating system. Okay. So what happens then, when definitely the next process, the process has already been given the permission to go and get the resource, it will jump in to get the resource. But when it jumps in, suddenly it finds that P1 or the process 1 hasn't left it yet. It's still using it. So naturally, there will be a deadlock. I try not to take you deep inside at this stage because, as I said, in subsequent chapters, we have to go deeper. Okay, we are just an introduction part here. But keep it. Well, this is something that you are already familiar with from your, as I can remember, CSI 104 course. The generations of computers. The important things were the vacuum tubes, but they were still plug boards. So, no OS. Transistors, because multiple vacuum tubes were put into a transistor. And then we had the mainframe computers or batch systems. This is the OS, the first OS was batch system. Third generation computer was the introduction of ICs, the simple ICs. Okay, we used to call them SSI, the small scale integrated circuits, SSIC, and multiple.
Small scale
But
interface seekers SSICs.
Our modern machines are the fourth generation machines. These machines that we are using every day, these are fourth generation computers. Now, these machines have multi-programming as well. But in the third generation computers, we had multi-programming. It was the first time that we were using the multi-programming concept, because in the second generation was still monoprogram machine. That means only one program. Well, they were multi-programming in a sense that you could run multiple programs there, but at any given point of time, if you start a program, you have to finish the program before you can move and start the next one. But in multi-programming, true multi-programming environment, you have the opportunity to swap the CPU, swap the processes on CPU. So that is exactly what we were doing, swapping processes on CPU. And later in personal computers, we switch CPU from one process to another process. That is a difference in the early multi-programming, the third generation, where we had some highly influential, wonderful, very stable and strong platforms like Unix, Multics. These were the two real good ones that even to this day, in a modern OS, many features, many sophisticated features are basically replicated from the Unix and Multics. The fourth generation computers are the personal computers. Personal computer came in 1981, and in 1981, first PC, the personal computer, the hardware part, was brought in the market by IBM, and Microsoft gave the DOS, MS-DOS. It was still an old-fashioned black and white, as I say, call it. No, well, it has to be black and white because in those days, because I used my DOS. I used DOS. In those days, we didn't have a mouse. Well, it may sound strange to you, but we didn't really have a mouse. The keyboard was the only thing that we had in those days. I didn't use the mainframe computers, but I've seen it when I was just kind of like in the 4th grade or 5th grade. I saw in an engineering university. So I saw this big IBM mainframe computers, which are basically big machines. Those machines didn't even have keyboards. Okay, yes, you heard it right. For the time when I started using the first computer, when I was in the high school and later university, the early part of the university, so we used DOS, and we didn't have mouse. Then came mouse. So that is the timeline of OS. And as we understand from DOS, everything started evolving very fast. Okay. Technology also took turns here and there, especially around the year 2000, there was another big shift. And in between, there were shifts everywhere. And also, the devices were changing. We started having different kinds of electronic devices, not necessarily just a personal computer. We ended up with a smartphone. It was a very recent one. So we ended up with smartphones. We ended up with all kinds of smart gadgets. We ended up with the washing machine, the electronic appliances, the home appliances. So each of them, they had a different microarchitecture for the hardware. So naturally, to fit that microarchitecture and the underlying hardware, and to serve the purpose to serve the machines, these different machines to serve, we had to modify those operating systems. But still, essentially, the operating systems, they do the same thing. They facilitate the interaction between the user apps and the underlying hardware. The fundamental thing is still the same. So let's take a closer look at it. Well, they're all things that you can see. No OS, as I mentioned. There's no point of talking about OS because we didn't have any OS. It was all plug boards, right? It's all plug boards. And everything was in machine language. The next one was the second generation computer, where most operating system was FMS, Fortran monitor, Fortran monitor system. In fact, Fortran was the first high-level programming language introduced in second generation computers. Fortran and COBOL, too. There were two of them, the earliest high-level programming language. COBOL and Fortran. Version used to be used for research purpose, scientific research purpose, and COBOL for accounting. I still remember. The FMS, the Fortran monitor system. Whatever they were basically working with the same principle. You start a process,
Mấy cái này học rồi mình
you
đem
have to
anh
wait
em mình regen đó rồi.
until the
Giờ
process
thầy giới thiệu vậy nữa.
terminates or voluntarily exits the RAM. So there was no way we could interrupt the execution of the process that you have already started. That is the true nature of batch systems. Remember this word, batch systems. You will be finding it everywhere, even in the second chapter and many other places inside this book. Batch systems means you start a program and you have, from that point on, you have no power to terminate it. Not like our responsive systems. Our PCs, the personal computers, the fourth generation computers that we use, are essentially interactive. And they're interactive because they're interactive and responsive. Responsive because we can, and multi-programming, because we can toggle from one program to another program. At the same point of time, most likely at the very moment, this very moment, you think about your computer. How many programs are running? How many processes? In fact, when they're running, we call them processes. When they're loaded in RAM, we call them processes. So how many processes are running at this very moment? You go to your task manager, take a quick look, and you will see. So you're running all these processes at the same time, but you don't have to wait for one process to finish its complete execution. Right? You can easily toggle from this one a little bit, that one a little bit, that one a little bit, that one a little bit. Back and forth, back and forth. So the batch system was completely different. As you can see, this is the IBM mainframe machine, the earlier IBM mainframe machine. So where is my keyboard? There's nothing called keyboard at that time. Okay? So no question. It was all about card. And you get the output in a tape. And you put the tape there, gets printed out. The card they are referring to, if you can Google, punch card. When we were young, we used to play with these stacks of punch cards. So the punch cards were the only storage of data, portable storage of data. Okay? So punch cards, you can see, you can Google with punch card, and you can see the images, perforated cards with plenty of perforations. These perforations indicate a pattern of zeros and ones. So this was what we had. The OS in these machines were sitting right here. The main machine, the processing machine, this is the input machine, it's the output machine. And you need someone to manually and physically transport them from one machine to another machine. Now, when we have the operating system, this will call the batch processing. FMS is still the same, Fortran monitor system. It also worked in a batch way. As you can see, the stack of cards, and if you want, you can shuffle those cards, but if you want to go to this card, this line, then you have to go through all of them, all of the previous ones. The third generation computer, as I said, it was the first time they introduced the word multi-programming. Okay. Multi-programming. But in those days, the multi-programming was working in a slightly different way. Because multi-programming literally meant that we could actually put multiple programs on RAM at the same time. And we were swapping them in and out. And at any given point of time, we asked our PC of the CPU to go and execute one single task. So that is exactly how it worked. But in that era, it was the early days, I'll say. These are the early days, very early days, early multiple. We had two giants that were born, Unix and Multics. Multics was a highly influential. We'll talk about the Multic structure that influenced the development of today's Intel processors, Intel chips, and Unix in so many ways. And Unix was the first one that facilitated the real-time sharing of data. In those days, we didn't have anything called server. Yes. Remember, World Wide Web came in 1990. In those early days, and it was conceived, Internet was conceived in 1984. So we are talking about 1965 to 1980, the third generation computer. So right where we didn't have, but the Unix, even at that point of time, gave us a platform for sharing data in real time over a network. The network was not an internet network, but it was a LAN, local network. We had to learn Unix. I learned Unix at a very early stage, just a little bit. Okay. When we learned C language, we had to learn the Unix. Because if you want to work in an office environment where they were using, a handful of offices were using computer in those days, they had the LAN and a co-working place where they could share in real time some files and folders. That is exactly where they had the Unix platform. Unix OS. So, and Unix, the most important thing is today we are working with Linux. Linux was born out of Unix. Linux was born out of Unix. Even to this day, 80% of Linux commands come from the old Unix. So Unix was highly influential. Moving on, as you can see, multi-programming, what it meant. What it meant and how it differs is that it lacks the flexibility. What I mean, you use the word partition, memory partition. Memory partition is something like today we do it with our hard disk. Right? What do we do with the hard disk? In your hard drive, you have some partitions. Now, what are these partitions? Partitions are barriers, but they are logical barriers. You didn't use a brick or mortar to build a wall there inside your hard disk, or you didn't put a separator, some sort of physical thing to separate this part from that part. But this is a logical but strict division of the entire available space. And that is exactly what we did in those days on RAM. The thing that we do today on our hard disk, the same thing we did on RAM. But they were all of equal size. Now there are problems. These are all partitions because with a limited capacity RAM, as you can understand, the RAM in those days was hardly 32 KB, something like that. 32 MB RAM. So with that capacity of RAM, how much space you can afford to give in fact, if you want to divide it, then of course the operating system there, they will take up much of those spaces. And whatever space is available, they will split up into 2 or 3 partitions, just like our hard disk. And each partition will hold a program. And these programs, from time to time, were swapped out and stored in the hard disk and swapped back in whenever the CPU needed them. That was the way these early multi-programming systems were run. But even in those days, a new concept was introduced. As you can see right here, if you carefully observe it, of course, we understand these multi-programming things going on, but look at the combined one. I understand that A must be waiting when B is running, A and C must be waiting. When C is running, A and B must be waiting. That part I understand. This wait part I understand. But how about that? Why? Because this is a CPU view. Running means CPU is currently executing program A or program B or program C. You can see clearly there are 2 different phases. Later on, we will get to understand that these are the phases that we will call computation mode, and waiting is IO mode. So that means your CPU is busy. CPU is busy sometimes doing the computational jobs, which casually we call busts. The CPU bust that refers to the computation mode, where it is busy doing the execution of codes. And at certain other times, it is waiting for IO to finish. It is responding to IO, input, outputs. Even to this day, the CPU works in that way. There are some other modes of operation, but this is the essential mode of operation. CPU bust, IO bust, CPU bust, IO bust, CPU bust, IO bust. They alternate. Now, depending on the machine, different kinds of machines, the length of CPU bus and the length of IO bus may differ. For example, on our responsive systems, like the one that we are using at the moment, the computers, there's a short IO bus followed by a short CPU bus. Short IO bus followed by a short CPU bus. If you go to batch processing systems, just now I mentioned the word batch systems, there's a short IO bus and a long CPU bus. Short IO bus, long CPU bus. If you go to real-time systems, we'll talk about real-time systems very soon, like ones that we use in the military hardware. It is short CPU bus, long IO bus. Short CPU bus, long IO bus. So this is, it depends on what kind of machine and what is the purpose of that machine. So many different factors. But this idea that the way that CPU should work was conceived first in the 3rd generation computer. Finally, as we reached the 4th generation computer, as I mentioned, it all started, with IBM PC, and Macintosh also jumped in, Apple. And essentially, IBM stepped back, and it was Apple versus Microsoft. Okay, until recently. So I started my first one, my first experience with operating system was here with the DOS, disk operating system, MS-DOS, and that was the first one that was launched by Microsoft to support PC or personal computer. Then I have seen all these developments. In those days, no mouse. The GUI came, still no mouse. Then Windows 3.x came, mouse. Why? Because there was two things. One is the GUI. GUI means graphic user interface. That means the Macintosh, the first one, they introduced this user mode concept. MS-DOS didn't have the user mode. In fact, even to this day, you have your MS-DOS running on your computer if you're using Windows OS. You go to the command prompt, the shell, the Windows shell, which is basically the kernel of your current operating system. That is the DOS. You go and Google, type MS-DOS, and look at the pictures, and you will understand why I call it black and white computer. Well, yes, it is. There's a black screen and everything getting typed out in white letters. So that's it. That's what we had in those days. But they were high speed. They were really high speed computers. Come on, I mean, that's what you love, because you're interacting directly with a kernel, and you will see it when you go to do the labs later on, because you'll be using a shell. When you use a shell, and you can basically use a shell to do anything that you want to do on your computer that someone else could do by clicking the mouse on a Windows environment. Okay, so you can do whatever you want, but you will see that you can do it more efficient and without losing any time. The response time is higher. Why the response time is higher? Because you are interacting directly with the kernel. But if I click the mouse, and I click the mouse on the app, then the app gets in touch with the kernel, then the kernel gets in touch with the underlying hardware, and then it gives a feedback, gets the result, and hands it over to the user app. The user app will finally hand it over to the monitor and update the monitor, and then I will see it. So it does take a little bit of time, considerable delay. But that is okay, because the problem with the black and white computers, those command prompts, is that you have to remember a lot of commands. So it's a huge load on the memory. So to reduce that load, after they introduced GUI, after Macintosh introduced GUI, in 85 to 95 came the concept of WIMP. W-I-M-P. Windows icon menu pointer. And with this pointer, we had the mouse. Okay? And we are lucky to some extent that as I talk about these things to you, that I can think about my old days, that we actually went through all these things. My first Windows was Windows 92. I don't remember much about that, but I do remember about 95, which I used for a considerable period of time for switching to 98 and then 2000 and XP. XP was a phenomenal success. And XP was so successful, Microsoft Windows XP was so successful in the market that Microsoft itself had to kick it out. Yes, sometimes the corporates do all these kind of things. because no one wanted to buy any other product from Microsoft, the upgraded version. They all wanted to stick to XP. With XP, they introduced virtual memory management and also a couple of other features, key technical features. The most important bit, virtual memory management. Then we go to talk about memory management later in another chapter, chapter 3. And we'll talk about virtualization of memory. And that was first introduced on the XP. I used XP for 10 years. Long time. I think more. So that is more or less the way the things have evolved. And they have written Unix right there. I think they made a mistake because Unix didn't come at that point in time. After it was not Unix. I think they meant Linux. Linux was born out of Unix. All right, so that is the way we keep changing. So let's go and take a look at the zoo, a place that we all love to go to. The operating system zoo, in fact, it is, because at the moment you're sitting inside your study room, you just look around and you have a smartwatch there, you have a smartphone there, you can see your AC machine, you can probably see the micro oven in your kitchen over there. OS. Everywhere. Remember right at the beginning what I said? Any interactive electronic device. Interactive electronic device. Because when we use the word device, we actually refer to a combination of hardware and software. Isn't it? So we have a combination of hardware and software that we usually refer to as a device. So if it is an electronic device and it's an interactive one, that means it receives inputs in some forms, not necessarily through keyboard, in some forms, and it generates an output of some sort, then it is an interactive electronic device. So if there's an interactive electronic device, rest assured there must be an operating system in operation right in the heart of it. Okay, so that's how we end up with diverse range of operating systems. And more so because for all these underlying hardware, they have different microarchitectures, they have different topology, they have different infrastructure, their microarchitectures are different, and they serve different purposes. So naturally, the OS that needs to be compatible with them must change as well. Okay. Batch processing systems. Just now we mentioned batch. It all started around the second generation computer, right? It's now multi-programmed. Multi-programmed doesn't necessarily mean that you can switch, but it's still pretty much the same batch system. You start a process, you are not supposed to interrupt it, and you have to wait until it voluntarily terminates or exceeds. So that is a batch processing system. We still have it, but we can run multiple programs. In the older times, it used to be just one program. Now we can run multiple programs. The most common one of that, the common applications that you can find, they have given you some examples right here, but I'd rather give you another example. The ATM, the automatic teller machines, where you go to withdraw your money. Well, you think about it, you go there and you press the button and you log in, you swipe the card or you punch the card and type in your password, and there you are, you have a few options, right? Always the same options. Good. So you actually went there to withdraw money, but mistakenly you pressed the wrong button, check balance. Immediately after pressing the button, you say, "Oh my God, I made a mistake." So there is no escape. Now you can't go back because by pressing that check balance option, you've actually initiated a process and you have to wait until the process is completed. The machine will display your balance, account balance, and most likely ask you if you want to do another transaction, yes or no. Some of the machines won't even do that. They will simply spit your card out and you have to reinsert your card to reinitiate another transaction. And hopefully this time the correct transaction. So that is how a batch system works. Another example outside of these, whatever they're given here, is it's still valid inside the industry, inside especially in automobile industry, where you have the large scale machines, and not only automobile industry, food processing university industry, then kind of dairy industry, dairy production, dairy products, everywhere. So essentially there is an assembly line. You put the raw materials on one side of the production line and you switch on, and then you wait. You don't have to touch it. You don't have to do anything. You don't have to interrupt it. The machine on its own, in a logical, sequential, predetermined way, it will from this machine to that machine, that machine to that machine, that machine to that machine. And finally, at the other end of the production line, you see 5 minutes later, 10 minutes later, or 20 minutes later, the finished product, neatly packaged, is delivered. So your input was raw material, and your output 20 minutes later was the finished product, neatly packaged, well packaged. So that is what another example of batch systems. So we understand how it works. The next one is a microkernel. Microkernel, although this says server operating systems, well, server operating system essentially depends on microkernel. Microkernel is a concept that was first conceived by Steve Jobs. Yes, Apple. Microkernel literally means that keeping the kernel as simple as possible. Why? Because whenever you need kernel to intervene, to facilitate some kind of interaction with underlying hardware, the things will slow down. That's the common nature, right? Every time, even when a normal app is running on your computer, as long as it is running on your computer, like you're clicking here and clicking there, and some simple things are getting executed, fine, no problem. But the moment you want to save a file or open a file, you will see it does take a little bit of time, because that is a system call. We will learn about system call later. The system call means a service request that you send to the kernel, and then kernel will respond to it by getting in touch with the underlying appropriate hardware, in this case, the hard disk, retrieve the data from there, and then hand it back to the user mode. The user mode will hand it back to the appropriate app, and the app will display it on your screen. So it does take a little bit of time. But a point here for the concept of microkernel is that in this architecture, it's basically an architectural design, architectural concept. that they decided to keep most of the non-essential tasks in the user mode. Now that raises a question, naturally. So what do you think is essential task of the kernel and the non-essential task of the kernel? Well, it's not easy to answer, honestly. And that's why microkernel concept is not very popular, except in Apple. You know why? Because Apple gives you both the hardware and the software, unlike Microsoft. Microsoft, until recently, they try to give you the Surface computer or something in recent times. Microsoft has traditionally given you the software. And this software run on so many different hardware platforms coming from different hardware vendors. Dell computer, Acer computer, Asus computer, I mean, you name it. So the problem is with Microsoft, they couldn't really introduce this concept of microkernel because if you are giving hardware and software together, you're developing your own hardware, and that hardware can only respond to your software. Then you design the software in such a way that its kernel will be super light. Because that's it. If you can keep minimum tasks or minimum codes inside the kernel, that means most of the other non-essential codes from the kernel will now run in the user mode. And anything that runs in the user mode is super fast. The moment, as I say, the moment your app tries to access the underlying hardware, it will have to go give a system call, or it will send a service request to the kernel, and things will start slowing down. So that was what they introduced. But in the server OS, we accepted that one. Because with the server, we do need microkernels. Because microkernels do facilitate, because server is multi-user. Multi-user means like PC. PC is designed for single-user PC. We call them single-user. PC is not designed primarily for multiple people to work together. Personal, that's why I call it personal computer. Your computer is for you. My computer is for me. Okay. Whether we are connected over the network, that's a different story. But it's a single user computer. But a server is not a single user computer. It's server because multiple users, most likely hundreds, thousands, millions of users, by using that machine at any given point of time. The multiprocessor operating system. The multiprocessor operating system, as the name suggests, is essentially a multiprocessor device. What is a multiprocessor device? Multiprocessor means multiple CPU. As simple as that. Okay. These days we have it like multi-core, dual-core. So naturally in multiprocessor systems, if you have a multiprocessor, the high system throughput, high performance, because parallel processing. Two processors, processor 1 and processor 2. Two processors are running parallel to each other. So naturally, the throughput or the output will be much enhanced, high availability. That was also, if you want to have an operating system for that kind of platform, that operating system must have the capability of efficient, I should say super efficient resource sharing. How will it share the common resources to two processes at the same time? It must be more efficient in terms of the algorithms embedded. Then we come to personal computer. In personal computer, we all know personal computer. We have many I/O devices, and we have the interface to single user, as I said, unlike server. And one of the key things about personal computer is about its multi-programming. And this is where we started. Well, you see that they didn't really mention multi-programming because when personal computer first came to the market back in 1981, as I said, the IBM was the first one to launch PC, and it's the Microsoft that gave MS-DOS. MS-DOS was not supporting multi-programming. You could only run one single program at a time. At any time, you could only run one single program. So later it became multi-programming, but this multi-programming concept is totally different from the third generation computers, multi-programming computers. Real-time operating system, I give you the example, then you will understand that how important it is. And as I've said, these are the ones where we have longer I/O bus and shorter CPU bus. Hard real-time systems are the military hardware. For example, the missiles. Ballistic missile, the cruise missiles that you fire to hit an enemy target at a supersonic speed. Okay? Intercontinental ballistic missiles, ICBM. Now, they have an OS there because you control the flight of these missiles. But there should be zero margin of error. Well, you fire a missile and suppose we hit the enemy target, and then suddenly you realize that your missile has hanged. What a funny joke, is it? Okay. So that doesn't sound good at all. That you fired a missile and the missile hanged. So that there shouldn't be any margin of error or any delay. It must be absolute. It must work with absolute precision. So we have a longer I/O bus and a shorter CPU bus with strict deadline and no margin of error. Okay, so that is something that we do expect from the real-time operating systems. The soft real-time systems, on the other hand, or multimedia systems, are the ones, one that comes to my mind is the drone. You have many others. Look at the multimedia experience in real time that you get. Drones. You know the drones very well. Some of you probably fly it on a playground, over a landscape, on a water body. And as it flies over the landscape, its camera captures the image and sends it to another port. Okay. Whatever the output device is. It could be on your computer screen, it could be on a pair of glasses. Sometimes you see the people wearing a pair of glasses or flying these devices. So naturally, it will capture the image in real time and send it to the output device. That is what is called the soft real-time system, where, yes, we don't expect a margin of error, but if you can still have slight margin of error. If some of these images get lost during transmission, That's still okay. It's not a big deal. Not like the hard real-time system where everything is absolutely strict and no margin of error. Embedded. Look around, you will see all your consumer electronics. In fact, the embedded things evolved in two different ways. These ones, the PDA, the palm pockets, evolved into modern smartphones. And they are no more embedded when you go to the smartphone. They are no more embedded at all. Okay, because we have RAM and we have I should say we have a RAM, we have a ROM, but they are still embedded. Yes, they are still embedded, not at all, because the Android is installed and Android will stay. I mean, you can switch it off, but if you switch it off, the Android is stored somewhere on, and they have a small amount of hard disk space as well. The other one, this true embedded ones from the consumer electronics that I was talking about, your washing machine, microwave, AC machine, etc. They are still embedded. And since they're embedded, everything is embedded. Both the software and the operating system are embedded on ROM. Okay? Embedded on ROM. And that's the reason you can't change it. If you are not happy with your washing machine, if you think that your machine is slow or not responding, then the only thing you can do is trash the machine and buy a new one. Don't try to upgrade or update your washing machine or microwave. Okay, that doesn't get. We also have smart card operating system, and the one that they didn't mention here was sensor. Sensor OS. Okay. So we do have different varieties of operating systems. But right here, the rest of the course, when we go to the actual main chapters, is we are still in the introduction part. In the main chapter, we will keep our focus on personal computing. A little bit, some here and there, reference the batch system, and sometimes a little bit, very little bit, about the real time. But primarily on PC, or personal computer, or interactive systems. Hey, what is JVM? I think most of you are going to study Java this semester. What is JVM? Why do we need it? Can anyone guide me on that? Java virtual machine. Okay, so you are just getting started. Probably you've taken one or two classes. I don't want to scare you at the moment. Now, JVM is something that you're needing if you want on your machine, if you want to run any Java program. At this point, that is enough for you. Okay? And the rest of the things you will learn in your Java course. JVM is sitting inside the JRE, Java Runtime Environment. Must have a Java Runtime Environment on your computer if you want to run any Java program. And inside JVM, we have an interpreter that reads lines of codes, byte codes, and converts them into machine-compatible codes and executes them line by line. All right, I will leave it there. This is another topic. So move on to computer hardware review, but before we go there, don't forget to take the attendance. Yes, that's what I remind myself of. Wait a minute. Okay, there we go. Attendance time is response. Jibao,
Yes.
Xuanmin, Xuanmin.
Yes, teacher.
Yeah. You look at your screen. Wang Poi,
Okay. Yes, yes.
Hui Chang,
Yes.
Wan Dung,
Yes.
Tian Wang, and Dui,
Yes.
Tong Kwa,
Yes.
Yan Lok,
Yes.
Han Chuan,
Yes.
Yan Fat,
Yes.
Nop Viet,
Yes.
Wing Chiu,
Yes.
Nyat Min,
Yes.
Chuan Kiet,
Yes.
An Thi,
Yes.
Qiu Chong,
Yes.
Hu Phuc,
Yes.
Hu Duc,
Yes.
Min Chien,
Yes. Yes.
Wang Lin,
Yes.
Han Nan, Wang Pai,
Yes.
Zhang Kui,
Yes.
Jia Kiem,
Yes.
Hu Hiu,
Yes.
Chong Tu,
Yes.
and Flowing.
Yes. Yes.
Only one student, that was Kian Huang.
Teacher, Thiên Hoài y missing.
Tian Huang, are you present?
Yeah. His mic have problem. Teacher, Quang Vinh.
Wait a minute. Okay, whoever has problem, the mic, immediately send me. My mic has problem. All right. Yeah. Good. Hey, all of you are others are present.
Teacher,
Yes.
Quang Vinh.
I think you're already present. Where is it? Present. Okay, present. Everyone present. Still, check your attendance immediately after I take the attendance. If you see for some reason some mistakes there, quickly alert me. Good. So back to where we were. All right, there we are. Just talk a little about get started computer hardware review. We already know about this hardware. Nothing special about these things. We understand that history actually something that comes from one human time. right? The buses is a new concept, and we'll talk about it. Of course, not a new concept. So just the connection, the pathways for data transfer, address transfer, and control transfer. CPU. CPU consists of two parts, essentially three. First is CU, control unit, arithmetic logic, and registers, n number of registers. That's what we do. And then when we talk about memory, we talk primarily about RAM and ROM. These two are talked about primary memory. ROM we don't talk so much about because ROM on a PC contains, it's a chip, contains a set of instructions that you can't delete. You can't overwrite. Okay? These are the set of instructions that will help the computer to wake up every morning when you click the power button, when you press the power button. So that's nothing much. So primarily our focus should be on RAM. And the I/O devices, we have a whole range of I/O devices, including, don't forget, your hard disk memory. It's also a memory, but your hard disk drive is actually an I/O device called disk. Okay, it's an input-output device. It's a storage device. Basically, we store the data there, and we retrieve the data, and we put it back on the processor. And we have the buses. So the most common architecture that we see here is this. This are all hardware. Sorry. Input, output devices. And then you have the memory, and you have the CPU. But you should notice that we have introduced another piece of hardware associated with all these external peripherals that we call computer peripherals. Peripherals. Okay. The monitor, the keyboard, the floppy disk, hard disk, and so many others. So these are all input-output devices, and most likely they even come from different vendors. And they work at different speeds. That is one of the reasons why we have introduced one of the some other reasons, of course, but that is one of the reasons. The difference in speed of performance between these I/O devices and the central processing unit and memory. They work at a certain speed, and these I/O devices work at a certain speed, a different speed. So that's one of the reasons we need this chip. These are chips called controllers. One of the most important things that the controllers do is to convert the bit streams that come as part of the electrical signal or digital signal, okay, from all these I/O devices convert these bits into byte blocks. Bit streams to byte blocks. We'll learn about these things when we go to the chapter I/O. We have a chapter on byte blocks. Okay. So why these byte blocks are important? Because when you convert them into byte blocks, this data, as you might call them, that, for example, right here, you have pressed A. Now, A means a digital signal, a sequence of 0 and 1. Okay, that will be sent to the keyboard controller. The controller will convert it into a byte block and will store it right here inside its buffer. Yes, all the controllers have a buffer. And then from the buffer, the CPU, when it knows that there is an input happened and an input output has happened. I/O has happened. CPU will use the bus to read from the buffer and transfer it to memory. Only when this byte block has been transferred somewhere on memory, then CPU's PC will read it from that part, fetch it to the CPU, decode it, and execute it. Fetch, decode, execute cycle. That's the way it works. So we need them basically because memory and CPU, they are always going hand in hand. And you know it very well because you go to buy a laptop and you ask the guy in the shop that how much RAM do you have? And he will tell you this, the RAM currently is 4 GB, but you can extend it to 2 more GB. And you wonder, wait a minute, if I can extend it, then why only 2 GB? Why not 4 GB more? Why from 4 GB I can't extend it to 8 GB? Well, the fact is the CPU will not support it. The CPU will fail to support, in fact, fail to map that 8 GB RAM. So there you are. And if you want a new CPU, it's better to go and buy a new computer. So they are connected to each other and they work at a very high speed, and that's why all they need are the registers. You still remember from your previous course, the CSI 104, that registers, the high speed things, are the most expensive, okay, with a minimum storage. And that's exactly what we have inside the CPU, and we'll see it in a minute. Now, when you go inside the CPU, this is what you see. And n number of general purpose registers. We call them general purpose registers because in the runtime, they store some vital information, all sorts of information about the current process, which is currently executing on CPU. Remember, in modern multi-programming computers, it's always switching. At this very moment, it's process 1, the next moment, process 2, the third moment, then process 3, and back to process 1. Okay, they're constantly, the CPU is being switched by kernel, following an algorithm. There's also an algorithm involved in it. Okay, so we call it the scheduler algorithm. So we'll learn about it in the second chapter, chapter 2. So following an algorithm, but they're constantly being switched. So at this very moment, if process 1 is running, then all the process 1's related information and data must be available to these general purpose registers. And then the next moment, the CPU is switched to process 2. So it will go to process 2, and it will go to process 2. The process 1's data will be saved back into another register, which is a kernel level register. We will learn about it, and that we call PT, or process table. We'll switch them back into PT, or process table. And what is the process table? Well, you are not supposed to see it because registers are not for the users to see, to look at, but still you can give a call to your task manager and go there, keep an eye on that. The task manager is a process table. And it will see in real time that how those values are changing here and there. These values are all coming from the registers. So if the CPU switches from process 1 to process 2, then process 1's registered data will be saved into PCB. That's called process control block, or inside the process table, PT. And process 2, which is the new process which is about to start execution, its data or the information from that process table will be brought back into this general purpose register, be loaded into this general purpose register. And only after that, the execution starts. CPU will start reading the codes of the process to start executing. So that is a way it works. We will get back to this slide and we'll continue with this one. Remember, slide number 31. All right? So please remember that. Number 31, and we'll move ahead. Tomorrow we have a class. Don't miss it. So see you. We stop here. I need to take a 1 week break before the next class. And see you tomorrow again. All right? Thank you very much. And we'll see you tomorrow.
Bye, teacher. See you.
Bye.
Bye, teacher.
Bye.
Bye, teacher.
Bye.
Goodbye, teacher. Have a good day, teacher.
Bye teacher.
Yes, same to you. Have